Thank you very much, and thank you for the invitation. It's very nice to be back in Bonn. I've spent a big part of my life here, so it's nice to see this place again. So I wanted to tell you a bit about small deviations of Gaussian multiplicative chaos and the Sinh-Gordon model, and hopefully you will see that they are connected. Okay, let's first start with correlated fields. So I guess most of you know this, but I wanted to just recall. So if you have a log correlated field Z, let's say on the torus, is something where if you take expectation of the thing at two different points, then and here of course I'm abusing notation heavily because in principle this point-wise evaluation is not well defined. If you take expectation at two different points, you get some logarithmically divergent quantity as the points approach each other. And okay, then you have some nice thing where okay, ask that this remainder term here is in HS for H sufficiently large. And okay, the prototypical example of this is the Gaussian free field where you take the Green's function of the Laplacian. And as I just said, okay, the variance, if you take, I mean, this expression tells you that the variance x and z are the same thing, should be is infinite, so this function is not an honest function, but it's a distribution. And, it's a distribution, and it has slightly negative Bezo-Hölder regularity, which means if you smooth it a little bit, it will be in infinity.
Just one question to check. You put a minus in front of the log to check that we follow your talk.
Yeah. I don't know why I put that. I put a minus. I put a minus and a 1 over, so I think I did that. I should have remained with 1. Yes, it should be positive, of course. And there's more typos to further check.
You'll tell us if we have followed.
And okay, so this means, since this is not a well-defined function, it means that a nonlinear function, you cannot take nonlinear functions of this field. Okay, so in particular, you cannot take exponential. But okay, there is a way to resolve this issue that if instead of taking exponential, you take the stochastic exponential. This is formally given like this. And okay, depending on the size, so if you put a gamma in front of the field parameter, depending on the size of the thing, you have 3 regimes. So if gamma is small enough, you converge in L1 in probability, and then at some critical point, you will still obtain something non-trivial if you do further renormalization, and for gamma large enough, you don't really get anything. So we'll always stay in the subcritical regime here. And there, okay, if you renormalize in this way, so you smooth the field a little bit, so you get something that you can evaluate pointwise, and you multiply by something which looks like this, but okay, you just take an epsilon here, where you can check that this is exactly, up to an order 1 term, this is exactly this. And then you take the limit, and you can check that this is you get a well-defined random measure. Okay, so far so good, I think. So then you can ask a lot of questions about this thing, and in particular the thing that we're today interested in is small values. So when is the total mass of this measure very small? And so maybe, I don't know if it was the first, in which chronological order this was, but so there's 2 results which were known in the literature about this. So the first is in 1 dimension, so if you have a log correlated field in 1 dimension, then actually Remy obtained first on the torus and then on the interval an explicit formula for the total mass of this measure. And from this, from this explicit formula, you can read off the probability of the total mass being very small. And for Yeah, but okay, and in general dimension, there is no explicit formula, but there was still a result by Aubert-Lacroix, Remy, and Vincent Vargas, which says that the probability to be small is actually, yeah, it's tight. So if you condition the field to be zero average, which is important for this business, which I will comment on later also, is very tiny. So this is sub-Gaussian, in some sense, sub-Gaussian probability to be very small. And this is, of course, surprising because, in principle, this is exponential of a Gaussian. So you would expect, in some sense, log normal tails, but this is not the case. And this is really because of the fact that you conditioned your field to be zero average, as we shall see soon. And so they obtained this power 4 over gamma squared here, and then they have a logarithm, which depends depending on epsilon. Okay. So, okay, the Sinh-Gordon model, so the other piece of this title. Okay, so this is a probability measure. Oh, yeah, it's a model, so it's a probability measure which has path integral or integer. There's density given like this, so you take a Gaussian free field and then you tilt it in this way. So you put, and then you put a Lebesgue measure on the on the average. So the zero mode has the Lebesgue measure, and the rest is given by a Gaussian free field with a zero mean. And you look at it on a torus of size R. And I mark this in blue because I are interested in the case where R is very large. And then you give it a meaning like this, that you take the Gaussian multiplicative chaos with negative gamma, and then you take a Gaussian multiplicative chaos with positive gamma, and then you build this measured by this expression. So formally, this corresponds to this sort of path integral here. So this is why it's called the Sinh model, because if you compute if you take this action and you compute the equations of motion, you will get a hyperbolic cycle. And note, okay, so important thing here for us is that there is no mass term in the action, so there is no term of this form, which actually sort of tells you that this, there is very little, in some sense it means that there is very little to constrain your C integral here, so so you have to, it's really not immediately obvious that this is a probability measure because the C integral could be non-normalizable. So you have to do a little bit, even in finite volume here, to see this. And then you're interested in this so what we were interested in this case is the partition function, so the total mass of this measure. And okay, maybe let me first resume some known results in this model. So if you have so in the form factor approach, so sort of a more, a different kind of way to attack this model, this was constructed in infinite volume. So the correlation functions, I believe, were constructed by Kozlovsky. And then the massive model has been, I think, has been studied for a long time. So Bavaria and her Krohn have already, I think they have constructed this even in infinite volume already in the 70s. And then, okay, we gave a different construction in the massive case where it's much simpler with Francesco De Vecchi. And okay, so for, just wanted to comment, so the beta should be a gamma, again, to check that you follow. That for gamma squared bigger than 4, so gamma bigger than 2, this was shown to be trivial, so it was shown to be the free field by Bavaria and Galavotti, which is not too surprising because the Gaussian multiplicative chaos is 0 in this case. Yeah, so the construction in the massless case on the sort of an infinite strip was done by Gunnar Gnam and Nikolai and Vincent Vargas. And then, okay, in the hierarchical case, so in the sort of case of the branching random walk, Hofer and Michael Hofstetter obtained the free energy, so existence of the free energy. So this is sort of what I know of what is known about this model in the mathematics literature, but in the physics literature actually a lot more is known. So there, okay, if you define this quantity m here, which is given by this very complicated, very explicit expression in terms of the gamma functions and the charge parameters, so the little gammas, then you know that then the physicists claim that the correlation functions of this model behave in this way for large x and y, so they decay exponentially with this very explicitly known rate. And okay, because I was asked about this at some point, and actually it's an interesting point. If you plot this function, then you sort of find that this actually, in terms of gamma, it looks really like a sort of kind of similar to a parabola.
Can you lift the board a bit? I mean, it's a bit low.
Yes. Make this bigger so people can see. So this really looks like this is 2, then this really looks like a parabola. I don't remember exactly what maximum is, but it's somewhere it was about 4. Ask ChatGPT to plot this thing, it will give you this. Okay, but of course, yeah, so the physicists claim that this is the case, and then they also have an expression for the free energy in terms of this mass. Okay, but we are very far from understanding these things, so we just asked ourselves a much more simple question, which is, does the free energy even exist? So if we want to, so if we would want to prove this statement here, then the thing on the left better exists, and okay, we just wanted, so we don't even, yes?
Is it as a function of gamma or gamma square here?
I think it's gamma, I think, because I think at 2 is the critical point, so you should, wait, sorry. Yeah, gamma should be at.
Yeah, no, you're probably right, it's 2.
I think gamma squared equals 4 is the critical.
Yeah. Sorry.
So here you sort of go back to the free bits, so it makes sense. So what we were able to show with Jona and Modik was that if you look at the free energy, if you look at the free energy, it's basically bounded, but we don't. At the moment, we're not able to show that the limit exists. And okay, let me try to convince you that this is actually related to the small deviations question that I mentioned earlier. And okay, the first thing you do is to say, okay, you scale my torus back to size 1, and then there's a scaling law for my GMC which looks like this. And so if I do the rescaling, I obtain something like this. So then, then I will give you the theorem that we have for the GMC, and somehow I will later explain why this is related. So with Jona and Modik, we were able to show that the small deviation, so the probability of the Gaussian multiplicative chaos is to be very small, is actually bounded by this expression. So this is the same expression that Hubert, Remy, and Van Zan had, but without the log. And okay, we actually use a lot of their program to get this bound, the upper bound, and then for the Gaussian model, we also need to bound, need to know a lower bound and the probability of this product being very small. So this inequality here you can obtain by a sort of trivial manipulation. So in some sense, the lower bound on this is a bit stronger than the lower bound on this. Yeah, so then by using an argument, which I will explain a bit later, we will, we can also get the lower bound. And again, it's very important that the zero mean is, that the mean is zero of the field. Okay? So let me just comment on why the zero mean is important. So actually, if you don't constrain the field to have zero average, then okay, it will be a Gaussian normal random variable, and then the probability to be very small will just be the probability of basically this Gaussian random variable to be very negative. And this is a log normal distribution, so this will be given like a log normal distribution. This is given in this term. And okay, the reason why the zero mode being zero improves things is that in the determinant, so if you didn't have any renormalization, so if you didn't multiply by this factor, which is sort of zero, yes?
So your estimate hold for all surface or?
Yes. Yeah, so you estimate the probability of the total mass being. So we do it on a torus.
So on the last slide, I saw that it's the next step. So the average is 0 on the torus. So
Yes, yeah. So we do it on the torus, yeah.
So does it hold for all surface?
Well, we didn't try. I would expect yes, but yeah, we didn't really try, but we would expect so, yes. If we consider, if we consider a field with zero average, then we can, and we didn't have any renormalization, so if we take the normal exponential and not the stochastic exponential, then you can just apply Jensen inequality and see that this integral is bounded below by 1. So then the probability of being very small is 0, because it's deterministically bounded by 1, but since you have this vector here, that's sort of what gives you actually the possibility of being very small. And okay, so to go back to the Gaussian model and why it's related to small deviations is so this was the path integral that we sort of arrived on before, and you can change variables in this C integral to obtain something like this. So this is why you see this product arising here that I had on the last slide. And then you are by a sort of Tauberian theorem, since this is growing exponentially, this function here in the argument, r to this power times the GMC product, this will be, by a Tauberian theorem, most of the contribution to this expectation will come from the area where this is very tiny. So you can reformulate this in the sense that this bound holds is actually equivalent to this bound that I wrote in the theorem. Okay. So to prove, so let me say some things now about the proof, how we actually get to something like this. So to prove something like this, it's very convenient to have a certain class of log correlated fields, which are called star scale invariant or almost star scale invariant. So this is something that's very convenient, and it basically tells you that you can write your covariance functions in this way, which is where rho is some sort of nice, usually compactly substantial function, and the almost refers to this blue factor being here. So you have to you make this thing a little bit smaller when you're allowed to for almost star scale invariant fields. Instead of really, so star scale invariant fields would mean that this factor is 1. And these sort of almost star scale invariant fields were introduced, I think, by Arrow, Christian Webb, and Janne Junila to prove, because they're very convenient to prove decomposition theorems. And one of the reasons that this sort of expression is nice, that here you can very nicely decompose scales, so you can have you can decompose your field as a sort of large scale correlated part and the small scale correlated part, and the small scale correlated part will become independent very quickly. this should be a y. Again, check if there's one. Okay. So yeah. So then there is lots of decomposition theorems which have been proven. So the first result is that when you have a log correlated field on a domain and then you can decompose it as a star scale invariant field plus something which is nice and further continuous. So in this first result, they didn't really know. Yeah, they didn't really say anything about the independence. But okay, they say that if you're in a small enough neighborhood, then you can take this decomposition to be independent. Then there was another theorem by Johan Aro, Anton Gigot, and Janne Junila, which says that actually if you take a compact subset in your domain, then you have these things. You can take the decomposition to be independent on this compact subset. Yes?
How does that interfere with zero mean? Do you know anything about the mean of x?
No, I think that doesn't really. I mean, you kind of have to impose the zero mean condition on z, and then.
Well, my question was, what is the mean of x then? Is it 0?
No, I think not necessarily. No.
Okay.
Yeah, but it's not. I think it's not a. It's sort of in practice. This is not a huge issue. I think because you sort of look at them together, and then you will see later. I will maybe comment a bit. And okay, so what we're able to prove with Iona and Monik was that actually, okay, if you look on the torus, then you can take this decomposition to be global, so you don't have to take a compact subset. And okay, you pay a price which says that you don't have an almost star scale invariant field, but you only have the high frequency part of a almost star scale invariant field. And then you have some further continuous thing. Which, okay, in practice, this is not a big issue because anyway, you're interested usually in the high frequency part. And then we also proved a similar theorem saying that you sort of do a similar thing in Fourier space where you take you basically take a GFF plus some little perturbation. Actually, this should be a minus. And then you have a similar style decomposition, which will be convenient for later. But maybe I wouldn't. Yes, I would want you to take away this theorem if you take something away from this slide. And if you have this theorem, then you sort of have for a general class of log correlated fields, you have a nice decomposition. And this allows you to decompose your field into like a high frequency part, which is given like this, and the rest you put here. And the rest also includes the Herder continuous field part and everything. As I said, this bound is sort of straightforward to prove, so then you focus, for the upper bound, you only focus on this. And then, okay, you're interested in making this thing small, so then, as I told you, one expects that it's actually very hard to make this small. So then first you make this small by just choosing t large enough, so that this holds. And then you say, okay, this being smaller than epsilon is equivalent to this thing being less than 1, so now this factor here is gone. And now you do a zero mean lemma, so you exploit that now this sort of low frequency guy here has zero mean.
That was my question.
Yeah, so this is the part where you put, okay. Yeah, okay, so in this, I think here maybe you have a globally, just a second. Yeah, I think maybe in this, and here you're already taking the high frequency part anyway, so then I think you can take it to be zero mean. Sort of, anyway, you're protecting away all the, all the, so here, you can take, you're protecting away all the low frequencies. So here it sort of doesn't make sense because this in principle contains big scales, but this one doesn't. So this part should have zero meaning.
So in the next slide, the xt is high frequency?
Yes, no, this part is high frequency, so this is low frequency. Low frequency, so large scale. X lower t is, and this guy is high frequency, X upper t.
Okay.
And then, okay, so then you have a zero mean lemma, which tells you that either this guy is bounded below in some fairly large set, or there exists a set where it's sort of which may be quite small, but where this thing is very large, so bigger than 2 to the n for some n. And depending on which case you have, you study so you study different things. So in the first case, you just study the probability of this guy being small or less than 1, or maybe you should put less than 1/2 here. And then you have a correlation, concentration inequality, also due to these guys here, which we also had to tweak a little bit to get rid of the logarithm, which tells you that they behave like so you have the high frequency part has correlation length e to the minus t, so you have e to the 2t random variables, so they concentrate at speed e to the 2t. And since the t you have chosen in the right way, so then you have this sort of estimate here. And this is a concentration type inequality, or I guess what Offer would refer to as a large deviation estimate. Okay. And okay, in the other case, if you have this set where you have the field being very large, then you just zoom in on this set, and then you can no longer use concentration because the set is too small, so you don't have enough space to decorrelate. But your field is very large, so you gain a large factor in front, and then it's even harder to make this thing small. So then you zoom in on this set and you do another decomposition, and you do the same game again. So now you do everything at, again, higher scale, and okay, again you either end up at the first case where you can apply a concentration inequality, or you have to, again, go back to this case, but every time you do this, you gain a large factor. So at some point you will be so large that you can basically do whatever you want to bound this guy. Okay, or you can even say, okay, I will terminate at some point that will be infinite, so I cannot be smaller than infinity. Okay, and then you sum up all these events and you get the right bound. So let me comment maybe on the lower bound. I'm very fast actually. So let me comment on the lower bound. So the lower bound, we apply this Hausdorff formulation. So what does this say? So this says that if you have an expectation of this type, so you take an exponential of minus some function, and then you take the log after. And this is the same as evaluating this quantity on the right-hand side. So this is an infimum of all the measures which are absolutely continuous with respect to your original measure. And then you evaluate this expectation on this new measure, but then you have to add the relative entropy. So in this case, we sort of go back to the in some sense, to the Koch model and try to get a lower bound on the free energy. And okay, this is equivalent to getting a lower bound on the small deviations. Yeah, so then we just choose f in this way, and so to get a lower bound, the lower bound we want, it's sufficient, it's equivalent to getting a lower bound, an upper bound on this guy. So since this on the right hand side is an infimum, it's sufficient to choose the right nu. So we just have to find the right measure where this guy is bounded by some constant times r squared. Okay. Sorry, it's not Pui, it's Donska-Varadhan. So apply Donska-Varadhan. Yeah, so we apply, so then now we use the same decomposition where, okay, but with this, instead of decomposing into a star scale invariant part and the rest, we decompose into this free field part and the rest decompose into something which is covariant of this type. Okay, we project, again, we only take the high frequency for some n sufficiently large. So, in particular for n sufficiently large, this is positive, so it will be a covariance. And then, okay, we choose, we have to choose the right measure, so then the choice we make is, yeah, so on high frequencies we do nothing, so this is just the free field. And on low frequencies we replace the n squared by an r squared. So we make it small, so we make the variance smaller. And then we have to bound this quantity, so we have to bound both terms. So the first term we have to bound the f, so the f is this one. So we want to show that this guy actually only grows like r to the squared, as opposed to growing like r to the 2 plus gamma squared over 2. So why is this the case? Well, you can just compute the, so you take the low frequency, so you take the low frequency part and you compute. And then you find that you have this log r term here. So you now have made you made this expectation log r smaller than it used to be. So this will give you, once you plug this back into the GMC, this will give you this extra minus gamma squared over 2 factor. So this computation is here. So you get r squared to the minus gamma squared over 2 times some constant. And yeah, so then all you will have left is this r squared factor. And okay, then that remains to control this relative entropy term here. But the relative entropy term, okay, on the high scale, on the high frequencies you did nothing, so there is nothing to bound because the relative entropy is 0. And on the low scales, you just, yeah, again, you compute, so there is an explicit formula for the relative entropy of 2 Gaussians, and everything is tensorized, so and the relative entropy of tensor or product of independent random variable, independent laws is just the sum of the relative entropies. So then you just compute, and you get this sort of expression, and then you do a change. Basically, you just do a change of variables in the sum, and then you multiply and divide by r squared, and then you see that you end up with something like this, where you rescale basically you're summing over all the frequencies less than r, but now you change your variable, so you're summing only over frequencies less than 1, but with a finer mesh. So before you were on a lattice of size 1, now you're on a lattice of size r to the minus 1, and then you divide by r squared, and now you have this logarithm. So this is just a Riemann sum approximation of the integral for the logarithm. So this is r squared times this, which is fine. Okay. And okay, maybe let me say, yeah, now I have to talk for a long time about open problems. So open problems, so now we have bounds on the free energy, but we would like existence, so we would like to say that these things are not just bound from below by constant times, two different constants times r squared, but we would like to say that the constants are actually the same asymptotically. Yeah, so then another open problem is the construction of the Sinh-Gordon in infinite volume. Okay, then of course one would really like these integrability results that I showed earlier, but this is seems to be very hard. And then okay, the Sinh-Gordon model, where maybe one can ask similar questions, but this is, as far as I am aware, this is already currently being worked on. So yeah. Yes, so I think I will stop 10 minutes early. I'm sorry, I think I was faster than I expected to be.